Okay. So we want to convert z equals 2 plus 2i root 3 to trig form using radians, okay? So, let's do that real quick. Oh gosh, we don't even have any room for this. Okay, we'll put it up here. So part A. All right, so what's 2 plus 2i root 3? So what is r? So it's a square root, we already did this one, right? It's 4, correct? Square root of 16. 2 squared is 4. 2 root 3 squared is 12. So we get root 16 is 4. And theta is the inverse tangent of root 3, which is 60 degrees, but we want this in radians, so it is pi thirds. Okay? So then trig form, if I did like this, this would be easier. So trig form then is 4 times the cosine of pi thirds. No, that's not any better. This just makes it so hard to write because plus I sine pi thirds. Okay, so we want to find z squared. So in other words, we want to just find z times z, right? So that is, do you remember? So it's, so if that's z1 and z2, then it's 4 times 4 times the cosine of pi thirds plus pi thirds, or 2 pi thirds, plus I sine 2 pi thirds. Okay. Now, if we want to put that in standard form, back in standard form, what's the cosine of 2 pi thirds? Or in other words, the cosine of 120, right? Negative 1/2? Okay. So we get, 8. I was going to put 8. We get 16 times negative 1/2. And what's the sine of 2 pi thirds? Okay, so then standard form of that is negative 8 plus 8i root 3. That's z squared. Now what if I wanted z cubed? What would I do? Yeah, then I would take the trig form of this one, which is right, oh, that's a 4, right there, okay, and then times that by this one again, okay? What if I wanted z to the 8th? Well, then we're getting all sorts of crazy, right? So we need a formula to handle all this stuff, okay? And it's actually called, well, it's a theorem, and it's called Demoivre's theorem, okay? So basically it's this. So if z is some complex number in trig form, okay, then z to the nth power is simply this. It is r to the n times the cosine of n theta plus I sine n theta. Okay. All right. So what we need to do.
So is the n in the, is it times the?
It's times multiplying by theta, correct. It's n times theta. So it's like, again, cosine n theta plus I sine n theta, like that. Okay? All right. So we need to find, again, if we're going to number in standard form, like in example 1, we need to find r, and we need to find theta. And then we're ready to roll. Okay? We'll blow this up. Okay. So with example 1a here, so r is the square root of 2 squared plus 2 squared. Oh, sorry, I don't need that squared. So we get the square root of 8. And leave it like that. You can go to root 2, but just leave it as root 8 for now. Okay, what's theta? is the inverse tangent of 2 over 2, or 1, and that is 45, or pi fourths. Okay, so now our number in complex form then. Okay, so now for this one, all right, now we're already given trig form, so we want to find z to the 7th. So z to the 7th equals 2 to the 7th times the cosine of 300 times 7, which is 2100, plus I sine of 2100. You think, holy cow, 2100! That's what calculators are for, right? They'll actually do that for you. So what's the cosine of 2100? 1/2, which means the sine of 2100 is going to be root 3 over 2. What's 2 to the 7th? 2, 4, 8, 16, 32, 64, 128. Distribute. So we get 64 plus 64I root 3. Wee-haw. Okay, so if we think about what raising a complex number to a power does, it does two things. And informally we can see those things if we think of graphing complex number and its powers, okay? But it does this. Basically, okay, raising a complex number scales up the modulus, or the radius, and it winds up the angle. Okay, so if we think about it, right, so if we were to graph 2 plus 2i, okay, what does that look like, right? 2 this way, 2 this way. There we go, okay. There's your modulus, and you go from there, okay? Now, so if I raise that to the 8th power, like I say, then we go 8 times around, so there's 1, 2, 3, 4, 5, 6, 7, 8. That puts us right here. Okay? Right? If I go in increments of 45 degrees, because that's what theta is, right? So if I go 8 thetas all the way around, I get right back to standard form, and then I scale up that radius from the square root of 8 to 4096. So it goes clear out there. Okay? Then on part B, kind of the same thing, right? I go to 7th power. You go around, well, you end up to 2100, but anyway, long story short. Okay, and then our modulus, okay, goes from 2 up to 64, 2 to the 7th power. Or, I mean, well, up to 28. Okay? So, again, it winds up, so when we start taking those powers, we start going around several times, and each time that we raise that power, the radius gets bigger and bigger and bigger. Okay? All right, so now we're going to kind of go in the opposite direction. So now instead of finding powers, we want to find roots of complex numbers. Okay. All right. So why is 2 the cube root of 8? Because 2 to the third 2 cubed is 8. Why is negative 4 one of the square roots of 16? Because negative 4 squared equals 16. Okay. So definition now. So if some number w, a plus bi, is an nth root of z, or it is an nth root of z if, this is just a plus bi raised to the nth power equals z. Okay. And again, that's just like because 2 is the cube root of 8 because 2 cubed equals 8. So a plus bi to the nth, if that equals z, then a plus bi is one of the roots of z. Okay. All right, so how do we find the nth root of a complex number? Now we're going to, what it says here, we're going to gloss over some details, okay, because it can be really complicated. All right, but here's the deal. So basically it's this. So say we have, all right, so here is de Moivre's theorem right here, correct? Z to the n equals r to the n times cosine of n alpha in this case plus I sine n alpha. And we want to get back to z. So if we want to get back to z, it would stand to reason then that we would just take the nth root of z to the n, correct? Okay. Times the nth root of all that mess right there. Okay. Now, so if we get there then, all right, then this would be r to the n here. Okay, and then this would be the nth root of cosine n alpha plus I sine n alpha. And again, you don't necessarily have to know this. We're just deriving the formula that we're coming from. So if this is not clicking right now, don't stress it. Okay. All right. So it's pretty clear what to do with that part, right? The nth root of r to the n is simply r. Okay, that one's not too bad. But what about this mess here? And that's where we get into a problem. Now, if we multiply the angle by n, when we're raising the complex number to a power, it stands to reason that we should divide by n when we're finding the nth root. Okay? So then we're thinking that it should be this, right? And that actually is, okay, that's one of the roots though, but like I said, if only things were that simple. They're not quite that simple. And let's go to page 2 and find out why they're not that simple. All right, so the reason that they're not that simple is this. So the actual formula then is this right here. Okay. Now, why do we have the 2 pi k and all this n minus 1 and all that crap? Okay. And here's why. All right, when we take powers of a root, right, we scale up that radius. We scale up the radius and we wind up the angle, okay? When we find the nth root, we put that process in reverse. So we're going to take our radius, okay, and make that smaller, and we're going to unwind the angle. And these are Mr. Law's terms here, by the way. We're going to scale down the radius and we're going to unwind the angle. Okay, now scaling down the radius is not a big deal. That's the nth root of r, and that scales down our radius for us. Now the angle's a whole different animal, and the reason, okay, if you think about that last problem we did, we were at 2100 degrees, okay? We start finding nth roots of that, all right, and we start unwinding that angle, we're going to hit several angles along the way, getting back down to whatever root we need to get to, okay? So we have to account for each of those angles, what we call coterminal angles, okay? So that's where this comes from, okay? And again, so there are lots of angles that are coterminal with theta over n, and they all occur in periods of 2 pi, okay? All right, now, okay, so let's go to example 2 here, and let's see. It's actually simpler than it sounds. So here's the deal now. So we've got 8 times the cosine of 30 plus I sine 30, and we want to find the cube roots. Okay, so if you look at your formula up at the top of the page, okay. So now in this case, if we want to find the cube roots, then n is 3. Stop. N is 3. Okay. So then if we have z to the 1/3, right, then that's going to equal r to the 1/3, or 8 to the 1/3, or the cube root of 8, times the cosine of 30, in this case 30, plus 2 pi k. No, sorry, we're not going to go 2 pi, we're going to go 360 because we're in degrees. Plus 360 k all over n in this case, which is 3. Plus I sine of 30 plus 360k all over 3. I need to make that bigger. All right, so we're going to start with k as 0. So I plug 0 in for k, and I get okay, 8 to the 1/3 is 2, right? Times the cosine of, I get 10, correct? Plus I sine 10. Okay. If we do k is 1, then we get 2 times the cosine of 30 plus 360, which is 390 over 3, which is 130, plus I sine 130. And then k is 2, we get 2 times the cosine of 30 plus 720, which is something, something. 750 over 3, which is 250. Oh, hello, I gotta put cosine in there. So we get the cosine of 250 plus I sine 250. And those are your 3 cube roots. So now we crank those out. Cosine of 10. Now normally these will work out a little cleaner, okay? Well, that's all right. So you can like find on your unit circle and stuff. What's a cosine of 10? 0.985. Sine of 10. 2174. Let's go 217i. And then you double those. Okay, we won't do that. All right, cosine of 130. What's the cosine of 130, people?
.67.
Negative 0.67. We'll just go to hundredths here. And
6.4. Did I say 7?
oh yeah, you said 6.7. 6.4.
Yeah, sorry.
And then sine of 30. I mean 130. 0.77. Okay. All right, and et cetera, right? And that's how you find your roots. And then you distribute that too, and that'll give you your roots in standard form. Okay. All right, let's try the next one here. Okay, so we want the fourth roots of 81 times cosine of 300 plus I sine 300. Okay, so in this case, n is 4. Right. So again, we've got to do k equals 0. So that gives us the fourth root of 81. What's the fourth root of 81? Say 3. Good. So we get 3 times the cosine of 300 over 4, which is 75, plus I sine 75. Okay, there's 0. Now let's go k is 1. So we get 3 times the cosine of 300 plus 360, which is 660 over 4. Wait, no, that's not right. No, that is right. What is it again? 165 plus I sine 165. All right, let's do k is 2. So that gives us 3 times the cosine of, let's see, 720 plus 300 all over 4. It's 1,020 over 4, which is 200 and what? 255?
And like, because you're dividing by 4, you can just add 90 on every single time.
Okay, everybody hear Ethan? Okay, yeah, good. Okay, I was waiting for somebody to come up with that pattern, right? Since we're dividing by 4, we know we add 360 each time, but since we're dividing by 4, we just have to add 90 each time. So 255 plus 90 is 345. Thank you. And see what this does, okay, is this gives us all of our roots from 0 to 360 by doing from k is 0, 1, 2, 3 in this case. All right, that's going to give us all of our angles from 0 to 360, which makes life kind of nice for us. Okay, and then you can crank all that stuff out. Not too bad. Okay, all of these. Okay, So basically, all right, if you work these out to make a long story short, okay? So over here on part A, I've got 10, 130, and 250. If I actually just drew those, and I hope you see that each of these roots, that their modulus is going to be the same, okay? So when you crank all these out here, this one and this one and this one, okay, and you find R, okay, if you found R would always be the same, okay? But if we look at it, if we look at 10 degrees, that puts us about, well, sort of right there. If we look at 130, okay, that's roughly right there. And then 250, whoa, okay, I gotta make them all the same. I'm not making them all the same. 250 is like right around in there. Okay, and if we made a circle, right, that would basically split our circle into 3 equal parts. Okay, because we have 3 roots. Okay, now on part B here, okay, so think of our angles. So we're at 75, so we're roughly right in that area. We're at 165, right there. We're at 255, and we're at 345, right there. Again, all my moduli are the same. That forms a nice, easy circle, and these split it up into 4. Those are all perpendicular to each other. So it splits it up into 4 different, equal or congruent parts. Okay. All right, so far so good? Okay, let's do the last problem here and then we're done. All right, so we want to find, and you will definitely see problems like this on MathXL. Okay, so we want to find all the complex roots of the equation x cubed equals 125. Now, so we know we got three roots, right? Well, we know we can find one of them, right? One of them is we don't even have to do the trig form stuff. What's one of them? Right, it's 5. Well, negative 5. Right, because if x cubed equals negative 125, okay, then we get x is negative 5. So there's one of my 3 roots right there. But now we need to see, we're just going to put that off by itself. Now we need to see how to convert this, okay? All right, so we get x cubed is 125, right? Or is negative 125, sorry, okay? So, now that's going to be our modulus, okay? So with trig form, we're going to do this. So we get negative 125, all right, to the 1/3 power. And then we know we've got the cosine of 0 plus I sine of 0. Okay? And so now, to put it in for our root form then, okay, we get the cosine of 0, which is, what's a cosine of 0, by the way? Yeah. So we get cosine of 0 plus, let's go degrees, 360k over, in this case, n is 3. Yeesh. Plus I sine of 0 plus 360k over 3. Obviously, you don't need to make that. You can simplify that and just make it, 120k. Okay. All right, so we go k is 0. Now, what's that going to give me, by the way? If k is 0, cosine of 0 is 1, sine of 0 is 0, this is the one where I get negative 5. Okay, well, we already knew that one, right? So now let's go to k is 1. So that gives us negative 5 times the cosine of 120 plus I sine of 120. What's the cosine of 120? Negative 1/2. And what's the sine of 120? It should be root 3 over 2. Okay, and if we times that by negative 5, okay, so that gives us 5 over 2 minus 5i root 3 over 2. So there's my second complex root. Now we just do k is 2. So it gives us -5 times the cosine of 240 What's that? The conjugate?
Yeah.
Yes, in this case we can because it's cube roots. Good call. Okay, remember the complex conjugate theorem back in math 1010 or 1050? I can't remember which one it was. Okay, that if one imaginary number, if one complex number is a solution, then its conjugate also has to be a solution. Right? Remember that? Okay, but let's bang this out and show you that that is indeed the case. Okay, but Mr. Gus, nicely done. Nicely done. Okay? All right, so what's cosine of 240? What is it? Should be -1/2, right? What's the sine of 240? That should be negative root 3 over 2. So then this gives us 5/2 plus 5I root 3 over 2, which is indeed the conjugate of that one right there. If I had a gold star, Tanner, it'd be slammed right on your forehead right now, dude. Way to go. Okay? All right, so now, complex roots are kind of screwy, right? Can we handle them? Okay, just got to remember, you always start with k as 0, and you go up to 1 less than what n is on that. Okay?